All right, let's just dive right into this. When you look out the terminal window at a modern jetliner, it's so easy to just see a massive, heavy machine made of cold metal and miles of wiring. But to truly understand how these things actually work, we've got to shift our perspective entirely. Instead of a machine, I want you to think of the aircraft as a living, breathing organism, complete with complex biological systems. And in this explainer, we are going to explore the incredible anatomy of an aircraft. Which brings us to this absolutely beautiful analogy pulled straight from our source material. Electricity is the brain and nerves that command, and hydraulics are the muscles that execute. It's so spot on. In the aviation engineering world, aircraft systems are organized into what are known as ATA chapters. And it's fascinating, because Chapter 23 for communications and Chapter 34 for navigation, they map perfectly to the aircraft's senses and its nervous system. Meanwhile, Chapter 27, which covers the flight controls, acts as the powerful muscular system. It's literally a precise, synchronized orchestration of biology, just in metal form.
So here's our quick roadmap for today's explainer. We are going to kick things off with the nervous system, then we'll move into senses and voice, take a look at its eyes in the sky, flex the muscles, and finally wrap up with keeping it flying.
All right, part one, the nervous system, powering the machine.
Now, think of the electrical generation system as the plane's cardiovascular system, literally pumping vital energy out to every single extremity. What's really interesting here is how the architecture of the 28-volt DC system carefully isolates what's called the avionics bus from the rest of the electrical network. See, avionics are the sensitive brain components of the plane. We're talking about the navigation and communication computers. So by isolating them on their very own bus, aerospace engineers are protecting these really delicate high-frequency signals from all the heavy electrical noise that gets created by power-hungry components like mechanical pumps or motors. It is exactly like giving the brain its own purified blood supply.
And if we zoom in on the absolute micro level of this nervous system, we find some incredibly strict rules. To protect those sensitive signals, the coaxial cables carrying them have to be exactly 50 ohms, period. If there's even a slight mismatch, well, that can cause power reflection, which is technically called a high-voltage standing wave ratio, and that can literally burn out a transmitter. No way around it. Plus, the metallic shielding on these cables is grounded on one side only. If a technician accidentally grounds both sides, they create this thing called a ground loop, and that introduces a maddening electrical hum that completely disrupts the pilot's radio communications. Imagine being in crowded airspace. A tiny grounding error like that can effectively silence an entire aircraft. Moving on to part two, senses and voice, avionics and VHF communication. To interact with the world, the aircraft taps into this vast, invisible spectrum of frequencies. Navigating everything from simple radio waves to super complex digital pulses, the aircraft speaks to air traffic control over VHF radio, but it's also using 1030 and 1090 MHz for the transponder, a super high 1.575 GHz for GPS, and it has all these other dedicated bands for things like measuring distance and landing via instruments. Basically, each frequency acts as a highly specialized nerve pathway for the plane.
Now you might be wondering, why on earth does aviation still rely on AM radio, amplitude modulation, instead of the much clearer FM radio we listen to in our cars? Well, it is for an absolutely life-saving reason. See, FM has this physical characteristic where the strongest signal literally captures the frequency, totally silencing any weaker signals underneath it. AM, on the other hand, allows multiple overlapping signals to be heard at the exact same time. So think about a mid-air crisis. Air traffic control needs to be able to hear everyone who is broadcasting, not just the loudest plane in the sky. It's an incredibly brilliant safety feature that's built directly into the physics of the radio wave itself.
Okay, part three, eyes in the sky, navigation and positioning. Have you ever thought about how a metal tube flying through the clouds at 600 miles per hour knows exactly where it is in three-dimensional space? It all comes down to GPS trilateration, and the math behind this is just fascinating. Basically, a satellite continuously broadcasts its exact position along with a highly precise timestamp using a literal atomic clock. The aircraft's receiver catches this unbelievably weak 1.575 GHz signal and calculates the exact time delay from when it was sent to when it was received. Since radio waves travel at the speed of light, you just multiply that tiny time delay by the speed of light, and boom, you have the exact distance to the satellite. Intersect those distances from at least 4 different satellites, and you've got a flawless 3D location.
So how does the plane actually share that location with the folks on the ground? Let's compare the legacy transponder system to the modern ADS-B system. The traditional transponder relies on a physical radar dish on the ground, actively pinging or interrogating the plane. That process takes anywhere from 4 to 12 seconds to update the air traffic controller's screen. But ADS-B, Automatic Dependent Surveillance Broadcast, total game changer. It automatically takes that hyper-accurate GPS location we just calculated and broadcasts it out to the world every half second. No ground radar required at all.
Now, I want you to just imagine this scenario for a second. What would actually happen if the right wing flap moved faster than the left wing flap during a flight?
Let's find out in Part 4, the muscles, flight controls, and fly-by-wire.
So to answer that question, an uneven flap extension would cause asymmetric lift, which leads to a catastrophic roll. Not good. To prevent this from ever happening, modern fly-by-wire jets work a bit differently. The pilot's inputs are sent electrically to the flight control computer, which is our brain, and then that computer sends a precise electrical current out to electrohydraulic servo valves, the muscles. But there is this ingenious safeguard built in called asymmetry protection. If a differential sensor detects that those flaps are extending unevenly, maybe due to a mechanical bind or a hydraulic leak, it instantly engages a safety clutch. It halts all movement, completely freezing the flaps in place, which keeps the aircraft flying straight and level.
And this brilliantly illustrates the strict logic systems at play. Take the ground spoilers, for example. These are the panels that pop up on the wings right when the plane lands to kill lift and apply heavy weight to the brakes. For the computer to actually deploy them, 3 strict and logic conditions must be absolutely true at the exact same moment. 1. The weight on wheel sensors must read true. 2. The thrust levers have to be pulled all the way back to idle. And 3. The system must be physically armed by the pilots. If even a single one of those conditions is missing, those panels stay completely flat. This logic entirely prevents a deadly accidental deployment while the plane is still high up in the air.
Which brings us to our final section, Part 5. Keeping it flying, maintenance and troubleshooting.
Just like human healthcare ranges from a quick daily checkup all the way to major surgery, aircraft maintenance scales up in a very systematic way. It starts down at the wide base of the pyramid with quick daily line checks right there at the airport gate. Then it scales all the way up to these massive C-checks at the very top, where the aircraft is essentially taken completely out of service, torn down to the studs, rigorously inspected, and rebuilt.
When things do go wrong, technicians have to dive in using their troubleshooter's toolkit. For example, let's say a pilot reports that their VHF radio just isn't transmitting. The mechanic doesn't just start guessing. They'll use a multimeter to check the electrical continuity of the push-to-talk switch right there on the pilot's control yoke. If that specific wire isn't grounding properly when the pilot presses the button, the radio literally never gets the signal to transmit. Mechanics also use specialized tools, like a Megger, to test the high-voltage insulation of cables, just making sure the plane's electrical nervous system is totally intact and completely free of leaks.
Which leaves us with a really fascinating thought to close out today's explainer. As aircraft continued to evolve from physical steel cables and mechanical pulleys into entirely digital fly-by-wire networks passing billions of data points a second, how will the mechanics of tomorrow adapt? How do you troubleshoot invisible data instead of just turning wrenches? It is a whole new frontier for aerospace engineering, and I really hope this explainer helped you understand the incredible anatomy behind it all. Keep learning, and we will see you next time.